All right, number 17. This is the fundamental rule of calculus, part 2. Derivative and integration undo each other. And you have to think of the hook comes from the bounds. So any constant to x, it's just plug in, and the answer is root x. Done. Number 18. Again, the derivative in that, know that you're plugging in the top bound and then the bottom bound. So when you plug in the top bound and take the derivative, it actually starts with 0 and then subtract, plug in 2x, and then we have a hook, and the derivative of 2x is 2. So this is what it looks like. So there's the first one. The second one, you have to start with the upper bound, subtract the lower bound you plug in, and then the derivative of 2x is 2. So it would be negative 2 root 2x, but you get the idea. Number 19. Again, plug in the upper bound, which is x squared. And then the derivative of x squared is 2x. So and the square root of x squared is x. So really, you could write this as 2x squared. So the square root of x squared is x. X times 2x is that. So understand the order of substitution. Then understand the bound, or the limit, how it creates the hook. So the derivative of x squared was 2x. All right, number 20 does not have a derivative in front, so you just have to integrate it. So for number 20, write it as t to the 1/2 dt, and this is what it would look like. So not the fundamental rule of calculus, part 2. So no derivative in front, so actually do the antiderivative. So that means you add 1 and divide or times the reciprocal. Then you plug in. So if you plug in x, when you plug in 0, the answer is 0. So you don't need to go subtract 0, and there's your answer. 21. So for problems 21 to 23, first of all, set up the integral that you see, meaning the area under the curve. And then don't attempt and don't need to evaluate it. It's just about the setup and the graph. So we're not going to evaluate. We're just going to set it up. So we're integrating from -3 to +3. And what are we integrating? 2x to the 2/3 dx. That's it. So the setup from -3 to +3, what am I integrating dx? Done. And don't evaluate it. You got it. 22. All right, for this one, I want to graph it. So y equals x over x squared plus 1. And it's from 0 to 4. So if I'm going to start this, let's just plug in 0. Like, let's get some endpoints here for our graph. So if I plug in 0, 0 divided by 1 is 0. So 0, 0 is on my graph. Plug in 4. And if you plug in 4, 4 squared is 16 plus 1. So it's 4 over 17. So 4 over 17 is what it is. What's the end behavior? So if you look, the end behavior, because the bottom is more powerful, the end behavior is 0. We have an x-intercept at 0. It's going to cross over. So this is what it's kind of going to look like. So that's the intercept. It's going to cross over, and then it's going to rise, but then it's going to come and it's going to approach 0 the further it gets. So we're integrating from 0 to 4. So this is the area that we're looking at. And then what would be the integration setup to be able to find that area? So we're integrating from 0 to 4. What are we integrating? X over x squared plus 1, right? Dx. All right, number 23. Let's see if we can sketch it. So 23 is g at y equals y squared plus 1. Now this one's a little different. So let me help you through this. And again, it's bounded by x equals 0, which is the y-axis. Y equals -2. And y equals 3. So let me show you what I would do. So that's x equals 0, y equals -2, and y equals 3. How would you graph this? This is not a function. So this is a sideways parabola. So think of the number that goes with y is always the k. So in this case, there's nothing adding or subtracting inside the parentheses. You don't even see parentheses. So nothing inside y. So the y value is 0. And what's on the outside, it's been inversed. This is what h is. And it does what it says. So at 1, 0, and because it's been inversed since the sideways parabola, it's tough to see. But at 1, 0, where x, the y value is 0 and the x value is 1, that's going to be like the vertex. There it is, 1, 0. And it's going to be a sideways parabola. We can find more points if you want. So if y is 1, y squared plus 1 is 2. So 2, 1. And it's symmetrical. So down here would be the same value down here. If I do it again, so here, this is 3. So what would happen if the y value was 2? 2 squared plus 1, that's 5. So there we go. Is there a right hand limit? No. So here, do you see how they intersect right here? So this bottom boundary, they're touching. On the top, they're not yet. So what's the next y value? Well, the next y value, 1, 2, would be 3. So 3 squared is 9, plus 1 is 10. So we'd have to go all the way. Where are we at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the way to 10, it'd be up here. So when y is 3, x is 10. This is like x equals y squared plus 1. That's what we're doing. And then shade this in with the boundaries. So it's awkward looking, right? So it's a little way different. So just relax. So it's not a function. So it's a sideways parabola. And we're finding the points where they intersect. We could also have done it this way. We could have taken y squared plus 1 and made it equal to 3. No, that's the x value, right? So here is y equals 3. Right. I could have just plugged in 3 and found the x value. And I could have plugged in -2 and find the x value. That this leads to the point 5, -2. This leads to the point 10, 3. That's what I have on the graph. Those are my points of intersection. Super important for the next unit as we go forward. So where are the points of intersection? And then shade it in. That's the area that you'd be finding. Now, what's the integration setup? You're integrating from -2 to 3. So it's like a flipped integration, right? It's the y values. So from -2 to 3, and you're integrating y squared plus 1 dy. And so you've inversed what we normally do. Again, I know it's super awkward, but you're able, whoop, there it is. But you're able to handle it with me, right? Together we can do it. So there's 23. 24, we're going to be a lot more of that in the next unit. And at the end of this one, I should say. At the end of this one, you're going to do a lot more of those. Not next unit, this unit, unit 6. Without a calculator, can you sketch and use geometry to evaluate? So I'm evaluating from 0 to 4. The absolute value is 3x subtract 2 dx. Let's look at that. So how would I graph that? So first of all, I look at the endpoints. So 0 and 4. So if I plug in 0, the absolute value of -2 is +2. Make sure you can see it. So yeah, 0 gives you 2, because the absolute value of -2 is 2. 4, if you plug in, 3 times 4 is 12, take away 2 gives you 10. 5, 6, 7, 8, 9, 10. And if it's a V, where's the vertex? How do I find it? Is I take what's inside the bars and find the 0. Like I make it equal to 0. So if you add 2 and divide by 3, at 2/3, you would find it. So 2/3, can you find 2/3? And then draw your V from 2/3. I mean, this would continue on like that, right? But we don't want that. We just want from 0 to 4. Shade in. You don't have to simplify your answer. So what would that answer look like? Well, there are 2 triangles, both above the axes. So this answer then would be the first triangle, half. Now this base is 2/3. And the height, we said, was 2 plus. Now this one's a little tricky, but what's the base of the next one? It's 1, 2, 3, and 1/3. I'm okay with writing it that way. So it's 3 and 1/3, and then the height was 10. And I don't need to simplify it. That's the answer. That's using geometry, using triangles. An area of triangles from 0 to 4. Number 25. In 25, you're integrating -2 to +1 to subtract the absolute value of x. See, the absolute value of x doesn't have any calculus rules to do the antiderivative, so we have to graph it in order to do it. So I always like thinking of the endpoints and the vertex. So if I'm going to graph this, if I look at one endpoint, if you plug in -2, the absolute value of -2 is 2, and 2 take away 2 is 0. And then the other endpoint, plug in +1. And if you plug in +1, you get 2 take away 1 is a 1. So 1, 1. Now, where is the vertex for this? So I have a better understanding of this if I wrote it as negative absolute value of x plus 2. So if I rearrange it, I can see h and k to be 0, 2. So you see 0, 2? That's the vertex. HK, 0, 2. And then draw your V only to where you need to. So yes, it goes down further. Yes, it goes down further. But there it is. Notice the negative has a reflection. It's been shifted up too. And now this area here, you're going to find the area of. So you could do it in different ways, but ultimately I'm going to do a triangle and a trapezoid. So the triangle here, the base is 2. So it's 1/2. The base is 2 and the height is 2. Plus, know that the whole area is above. This trapezoid, it's on its side. So the two bases, it's still 1/2. So what are the combined bases? So 2 and 1, that's 3. And then the height of it, because it's on its side, the height of it is 1. And there's your setup, and that's a great answer right there. Obviously, half of 4, 3 over 2. Put it together, you could say it's 3.5, or if you wanted to, but not necessary. 26. So in number 26, if f at 4 equals f at, find f at 4, if f at 2 equals 3, and the graph of the derivative is shown. So this is what's called a starting value problem. So the problem starts with what value? So the answer is it starts with 3. And then I add the integration of the derivative. And I'm integrating the derivative from 2 to 4. So it starts with 3. You integrate the derivative, and the x values go from 2 to what I'm looking for, which is 4. Now, how do I do this, the integration of that from 2 to 4? And I have to do it off a graph and find the area from 2 to 4. So if you're integrating, so again, that's the derivative. So if you're integrating from 2 to 4, I see a rectangle from 2 to 4. That's 1 by 2. So there's a rectangle here, which is 1 by 2. And there's a triangle on top of it, which is like half that size. But it is 1/2 1 by 2. It's also a trapezoid where the bases are on its side again, so it's 1/2, and then you get the same answer either way. Answer 6, right? Yep. So you could have done a trapezoid. I like trapezoids. So 3 plus 2 plus half of 2, which is 1. So add it up, it's 6. Done. 27. We're almost there. This is it. This is the last one. We're so there. So this is a related rate question, maybe. A spherical balloon is expanding at a rate of 5 centimeters cubed per second. Definitely a related rate. How fast is the diameter of the balloon increasing when its volume is 36 pi centimeters cubed? So identify what it is. It's a related rate. Now identify what each number represents. So what does 5 represent? So that's the volume of the balloon. So we're going to call that dV by dt, the volume. What I'm looking for is the diameter. So that's my unknown. And then I know the volume is 36 pi, and we have a formula to start with, which is V equals 4/3 pi r cubed. Let's look. So I just break down what I got. So the rate is 5 for the volume. I don't know the diameter, and the volume is 36 pi, and we start with this formula. So to the formula, we're going to take the derivative with respect to time. So the derivative of v is 1, but we need the hook dv by dt. Here, these are all constants except for r. So take 3 and you multiply. Notice the 3's cross out, and you got 4 pi r squared. That's the derivative, and then it needs the hook dr by dt. So let's see what we got. So dv by dt is 5. The radius I don't know, but it definitely connects us to the diameter. The rate of the radius. Do I know the rate of the radius? I don't. But you know what I can do? Look at this. With this formula, I could plug 36 pi in for v. Right? And I could find the radius when the volume is that. So the pi's divide out, multiply by the reciprocal. And 4 goes into 36 9 times, and 9 times 3 is 27. And then the cube root of 27 is 3. So the radius in this situation is 3. The question is, how fast is the diameter of the balloon increasing? Got ya. So it wasn't diameter. What we were looking for was d by dt. I'm looking for the rate of the diameter. So I want to plug that in for r. I do not know the rate. So again, the radius is 3. I'm going to find the rate for the radius and then translate and just double it to be the rate for the diameter. So I need this by itself. So 3 squared, that's 9 times 4. That's 36. Divide by 36 pi. That's now the rate. That's now the rate for the radius. If I want the rate for the diameter, well, what's the relationship between the radius and the diameter? Is you multiply it times 2, right? So if you multiply it times 2, that's now the rate for the diameter. So the derivative of the diameter with respect to time then is this answer here. So let's write a sentence here. So when the volume of the sphere is 36 pi, the diameter is increasing at a rate of, so when the volume of the sphere is 36 pi, do we have units even? Yep, centimeters. Centimeters cubed. So when the volume of the sphere is 36 pi centimeters cubed, the diameter is increasing at a rate of, and that's what this answer is, 10 over 36 pi, and this is centimeters per second. You could reduce it down, but totally not necessary. There's your answer. Hey, Mr. G Math over and out. I'm proud of you for doing your work. I know the review questions are challenging. We do it together. We figure it out together. You don't give up, and you fight to get the answer and get your work done. Mr. G Math over and out. Until next time.